So hello everyone. My name is Pierre, I'm a student with Generalist, and today I will talk to you about this work I'm going to be doing. It's called EoS-FM, and as you can guess, I will talk a bit about foundation models and about handling methods. So as a short introduction, in the last couple of years, there has been a lot of literature into foundation models for remote sensing, and the big trend that we can notice is the increasing in size of the models and the datasets. There is a good reason for that, is that in general, in deep learning, it has been proved time and time again that in most cases, when you increase the size of the model and the dataset, you get better results. And that's why typically for building foundation models, people try to do very large ones. When we try to do very large models, it's difficult to use supervised training because of multiple reasons. First, labels are expensive, which means that the datasets are typically small in size. And they are also typically specialized. So if you have a dataset, for example, for canopy height estimation, then your model will be specialist in that and nothing else. Whereas on the outside, we have self-supervised training with no labels, which means very large datasets for basically free. And you have general purpose context tasks like image reconstructions. And so typically when you want to build a large-scale foundation model, it's very easy, not very easy, but it's easier to use self-supervised training. However, we believe that supervised training still has some upsides. First of all, the training signal is very rich because the labels are typically annotated by human experts, so it contains a lot of information. And even though a single supervised dataset has a very narrow field of expertise, the whole body of supervised datasets in remote sensing has a very large diversity of different tasks. And so the question we ask ourselves is, how can we leverage this huge heterogeneous body of specialized datasets to actually find a general purpose? So some research effort has been made towards this goal. So we have a couple of models and datasets that try to find methods to train supervised foundation models. And we also have some self-supervised foundation models that also incorporate some labels in their training. But the intuition we had was to try and combine different specialist latent spaces into one that could be marginal. So here we have an example of two latent spaces. One is doing land use and land cover classification. The other one is doing canopy height estimation. And we were wondering, okay, can we combine these two into a single latent space that can actually distinguish all of these different classes and use this progression? So our proposed architecture to do this is using Ensemble. So the idea is to train a bunch of different specialist models. So here we have three examples. We have radar flow detection, we have RGB land cover classification, and we have infrared canopy height estimation. And use this ensemble of specialist models to actually perform tasks that each of them has never seen before. So the way we do that is first, we give the images of our new task to each of these different specialists. Then we use all of their features, we select them, we fuse them, and we give them to a decoder we train. This architecture, has a bunch of advantages. First, it allows for cheap training because the training of this is done in small parts. You just train very small models on very small data sets, so it's very quick. And it has also some other perks, like you can do federated learning quite easily, and it has way less hardware benefits. You can also do pruning for basically free because of this architecture in Ensemble model. You can easily just suppress half of the, just delete half of the Ensemble half of the specialist in Ensemble, and it will still work. And it can quite easily be adapted. Like for example, I've heard some people saying that not a lot of models are good on the cryosphere, and so if you train a bunch of new specialists specifically for the cryosphere and you add them to the Ensemble, it's expected that the model as a whole will improve in performance on this type of geography. So a quick overview of all the data sets that I've used to train these models. So there's a bunch of them. I will not go over all of them, but the idea is to show that many different task types, many different locations, etc. And in the end, we had basically, about 10 very high resolution data sets and about 10 Sentinel-2 multispectral data sets, and we have a little bit, a couple of SAR encoders also, but not as much. We still had some questions because we chose these data sets specifically for how easy they were to train on. we just looked at the TorchGeo library and chose a bunch of data sets that we deem to be interesting. But we can surely find a more optimal subset of tasks to train. So the first part of architecture is this band adaptation step, because as you might have noticed, we use a lot of different heterogeneous data sets. So these encoders that we train have all different input modalities. And so when we want to feed Sentinel-2 data to an encoder that has only seen RGB, we have to do some kind of band adaptation. So we do very simple rules, simply try to find the closest physically possible band that we can find. So if we have the exact same band, we use it. If we don't, we find the closest wavelength. And in last resort, if we really don't have anything that's close physically, we resort to cross-modality adaptation. So we give basically SAR bands to an RGB P-train encoder if we have enough loops. Then we have this encoder selection step, because as you can probably guess, most of these encoders will not be relevant at all for a given task that you choose. And so we have to have this dynamic selection algorithm that will choose, okay, for this new task, I want to use this encoder and this encoder, but not this one. And in order to do that, we assign to each encoder a weight, top K weight, that is trained at the same time as a decoder as a gradient descent. And then we perform top K on this weight. And basically, we just use a special regularization that allows us to set a K value for which the ensemble has the right to choose K encoders, and all of the other after that are being heavily suppressed. After this selection mechanism, we have this feature fusion step, where for every selected encoder, we extract the features. And then we have this very, very large feature map, which is basically the concatenation of all the feature maps. Numbers you can see here are the number of channels in the feature map. And then we fuse it using a simple convolution one-by-one layer, which is basically linear combination of all of these layers. We have actually tried to not use this and directly feed the huge feature map into the decoder, and it works. The performances are basically the same. But because of these huge feature maps, we have a very, very large decoder, very complex decoder, and so it's not very useful. So we decided to have this fusion. Some results. We tested on the Pangea benchmark, and as you can see, it works quite well. It's not the best node in all the cases, like for example, for Mados here, the Thermite model is actually way better than our little ensemble. But in most cases, it works quite well. And if we compute the average distance to best, which is the metric on the right, which is basically for each data set, we find the best model and then subtract best from whatever model we're looking at. We see that we basically have a performance that is on par with the biggest latest models, which is quite nice. And this actually also holds for 10% labels. So if we have a very label scarce situation, it also works quite well. And we also have a little bit of advantage over the largest models. So a little bit about this training. So this is a table of the training time of the ensemble. And as you can see, it's not very long to train it. If you have a single GPU, even a consumer grade GPU, you can basically train this. It takes 80 hours on one H100, which is still big GPU. And this training is very nice because if you have a lot of GPUs, you can do it very fast, but you can doing it in parallel. And if you have only a small GPU, you can do it still by doing simply training the different encoders sequentially. So this is quite nice. And I don't have some figures here, but for comparison, this is really way smaller training than the bigger bunch models. We have a couple of ablation studies. I have 3 minutes left also, so I will show you a couple of them. So first, we try to give the ensemble a budget for encoders, smaller and smaller, and see how the performance changes. And as we can see, we have multiple different types of tasks. For the task on the left, which is HAS band scarce, you can see that we basically have the same performance whether we use 22 encoders or we use like 4 of them. But for some other tasks, we can see that the performance still increases after, even like 15. So it really depends on the task. We perform also an analysis of which encoders were selected for which task based on the modality. So as you can see first on the left, some encoders were not at all selected for the Pangea benchmark at least, like the Mini France and the Sen12MS RGB. So it shows that probably some of them are actually useful more in general. And also on the figure on the right, you can see like the modality coherence of the selections. So in most cases, when you have a very high resolution data sets, it selects very high resolution encoders. And when you have Sentinel-2 data sets, it selects Sentinel-2 encoders. But in some cases, it doesn't work like that. Like if you look, for example, at the MADOS data set, which is Sentinel-2, you can see that it uses a bunch of very high resolution sensors, encoders, which is quite weird. So we try to investigate that a bit. As you can see, yeah, we have some problems like for MADOS, we use a lot of very high resolution encoders. And for AI for farms, which is in Sentinel-2 dataset, we use a bunch of SAR encoders, which was quite weird to us. And so what we try to do is to select ourselves a subset of encoders that is specifically very coherent modality-wise. So for example, for these two datasets, which are Sentinel-2, we selected only the Sentinel-2 encoders, and then a bunch of general purpose like ImageNet, for example. And we did not include in the Ensemble the SAR encoders, for example. And we tested this version of the Ensemble that was curated by us on these two datasets. And basically, we show that it does not improve. So even though this selection might seem completely incoherent, somehow the Ensemble actually managed to make it work. There are some discussions. Okay, almost at the end. In terms of computational efficiency, these models that we use are very small. They are convex Atto models, so about 3 million parameters, 3.4, I think. But we use a lot of them. So in the end, in terms of number of parameters, it's about the same as the normal information models. But because this is like an ensemble and not a single transformer that is really heavily optimized for parallel inference, the efficiency in terms of inference is not as good as I wished, but it's still not too bad, especially if you prune it. Also, a little problem with this architecture is that if you don't use this specific fusion step that you have to train with a decoder for a given task, you have a very large feature map. And so you cannot really use this as a standalone feature extractor. You have to use it on a task that you will train on. So to conclude, our contribution in this work, were to first show that it is, at least in our experience, possible to obtain general purpose representation from only supervised training. And we also introduced this specific model that is pre-trained and available online. That is quite fast and easy to train. And that has performance that is basically on par with recent baselines. And this specific train time training that is very nice, that allow you to reduce the size of the model on your task. And that's it for me. Thank you.
Yeah, for the nice presentation. So do we have any questions in the room? Yes.
Thanks for the presentation. You talked a bit about trading, that it's comparable or cheaper than other bigger methods. So what happens at inference time? Do you kind of pass a bit of this extra? I guess you do perform inference on this ensemble.
Yes.
So how does it compare to other larger models?
As you can see on this table, for example, we have GFlops for inference and FPS. And basically, if we use the full-size ensemble, which is the EoS-FM normal, it's about as fast as these larger 300 million parameter transformer. It's large, despite being much smaller, because of this ensemble architecture where you have to perform inference sequentially for all of these small encoders. So even though each small encoder is very fast, you have to do sequential inference for 22 of them. And so in the end, it's a little bit slower than if you have the VAT at the same size. So this is something I'm working on, but yeah, this is the downside of the architecture.
Maybe to improve this, you could add a step where you perform knowledge distillation on just one network so that you have your ensemble of specialists at test time, and then you can train a smaller network that will have a similar performance, but with a much lower complexity.
Yes, for sure. That's actually the next step I was thinking about doing. And actually, we are investigating knowledge distillation for not this purpose. So it would be indeed a very nice step.
Have you looked how similar or different are the representations you obtain with your ensemble of supervised models with some self-supervised models?
I did not, particularly because of this problem here. So typically, when you want to do these simulations, you just extract the features and you visualize them. But here, the features are very, very large. And contrary to, like, for example, a transformer model, which has one final layer with a nice visualizable feature map. Here, it's a convnet, which is basically a feature pyramid network, so I don't know if it's easier. But I could try to do it.
You could look at the relative difference of features of representations for one model. So if you take two inputs, you look at the distance for those inputs in data space of your ensemble model, and then on your on the self-supervised model, and you look how the distribution of those relative distances compare for every pair you can get.
Something.
Yeah. Okay. I will stop the discussion here, but then you can pursue during the break. So thank you, Pierre, again. We will pursue the